Hello, this is Richard Hammack's Calculus 1 course. We're in Part 1, Function Review. Today's Lecture 5C is on the natural exponential and logarithmic functions. This follows Lectures 5A and 5B, which reviewed exponential functions a to the power of x and their inverses, logarithmic functions, log base a of x. For any positive number a not equal to 1, you can define the exponential and logarithm functions for that base. It turns out in calculus there's one base in particular that's very significant, and if you use it, many equations and computations become simple, much more simpler than they would be with other bases. And exponential and logarithmic functions to that particular base are called the natural exponential and logarithmic functions. That's today's task. Our plan is to recall exponents and logarithms, and then introduce a natural base e, which is equal to an irrational number 2.71828182845 and it just goes on forever. It's a very strange looking base, and it's surprising that it's going to make our computations simple. But that's what it is. We'll define the natural exponential and logarithm functions e to the power of x and log base e to the power of x, where e is this strange number. We'll talk about properties of the natural exponential and logarithm functions. We'll talk about solving equations and what's called the change of base formula. Let's get into part 1, exponents and logarithms. If a is a positive number not equal to 1, you know that you can define the exponential function a to the power of x. And if you reflect this graph across the line y equals x, you get the inverse function, f inverse, which I've been calling a box of x. A box of x is the power that goes in the box, so a to that power equals x. But the rest of the mathematical world calls it log base a of x. That's the logarithm function to base a. As we discussed last time, logarithms satisfy a host of laws. Log base a of a to the x equals x. A to the log base a of x equals x. Log base a of 1 equals 0. Log base a of a equals 1. Log base a of xy equals log base a of x plus log base a of y. Log base a of x over y is log base a of x minus log base a of y. And log base a of 1 over y is negative log base a of y. That's just this previous equation with x equals 1 substituted in. So the log base a of 1 is 0. And finally, there's this really useful property that says log base a of x to the y equals y times log base a of x. And later in today's lecture, we're going to get a lot of mileage out of this property. So these are the properties of logarithms. Now we're going to define a special base for logarithms. As I mentioned before, there's a special number we call e. It's an irrational number between 2 and 3. It starts off as 2.7182818284590 and just continues without repeating. A very strange and mysterious number, but it's going to play a big role for us. Our big definition is that the function e to the x is called the natural exponential function. It's an exponential function whose base is e. What would it look like? Here's the graph of y equals e to the x. Now, e is bigger than 2, so if you think about it, this graph lies above the graph of y equals 2 to the x, but e is smaller than 3, so the graph of y equals 3 to the x is a little higher than the natural exponential function e to the x. Y equals e to the x is kind of squeezed in between y equals 2 to the x and y equals 3 to the x. So for instance, if you plug in 1, you get y equals e to the 1, and that's just e. It's about 2.7 right there. If you plug in 2, that's going to be e to the power of 2. E squared, it's 7 point something, somewhere in there, and so on. Let's talk about the inverse of this natural exponential function e to the x. Take the line y equals x and reflect this graph across that line, and you get its inverse, which is y equals log base e of x, which we might call e box of x. E box of x is the number that goes in the box such that e to that power equals x. More commonly, you might think about that as log base e of x. Now, this inverse, log base e of x, or e box of x, is a special logarithm that's called the natural logarithm function. So we have a natural exponential function and a natural logarithm function. The exponential and logarithm function to base e. And we have their graphs here. This logarithm, log base e of x, is so special that it has a special abbreviation. Log base e of x, or as I called it here, e box of x, is called ln of x. So whenever you see ln of x, that just stands for log base e of x. Log base e of x is ln of x. That's the natural logarithm of x. You're going to use it so often that you're going to get tired of writing log base e all the time. Just write ln. It stands for log base e. Some textbooks will drop the parentheses. They'll write ln of x as ln of x without parentheses, but I'm going to tend to write the parentheses, so I'll gray this out here. So in summary, we have a natural logarithm function, ln of x, log base e of x, also, which can be written as e box of x. And from the previous slide, here's the graph of ln of x and e to the power of x, the natural exponential and logarithm functions. Let's look at properties of ln of x. We're pretty familiar with exponential functions, so we know all of their properties. ln of x is a very important function, so its properties deserve mention. The domain of ln of x would be the range of its inverse, e to the x, so that's all positive numbers. So the domain is the interval from 0 to infinity. What about the range? That's all of the outputs you could get for ln of x, and that's going to be the domain of its inverse, e to the x. So its range is the set of all real numbers. That's all the possible output values for ln of x. There's also an x-intercept. Like any logarithm function, the x-intercept is 1. Let's do some examples. Ln of e squared would be e box of e squared. It's what goes in the box, so e to that power equals e squared. Well, obviously 2 goes in the box, so ln of e squared is 2. Ln of 1 would be e box of 1. What goes in the box? So e to that power equals 1. 0. Ln of 1 equals 0, and of course you see that here. Ln of 1 is 0. ln of the square root of e is e box of the square root of e. And let's write that square root as 1/2. So e box of e to the 1/2. What goes in the box? So e to that power equals e to the 1/2. 1/2. What about ln of 1 over e? That's ln of e to the power of -1, or e box of e to the power of -1. So what goes in the box? So e to that power equals e to the -1. Well, obviously -1. So ln of 1 over e equals -1. So in these examples, we've computed ln's of values that are all powers of e. So the computation turned out to be very simple. You'll often encounter things like ln of 10, say, and 10 is not a number that's a convenient power of e, so it's hard to think about this as e box of 10. Hard to reason this one out. But fortunately, we have calculators, and calculators have an ln button. So if you ever get to a logarithm you can't figure out in your head, you can, if you want to, reach for your calculator, punch in ln, and you'll get an approximation to ln of 10. So this is the number where if you raised e to that power, you'd get 10. But don't rely too much on your calculator, because if you do, you'll tend to forget the meaning of ln. And it's essential that we know the meaning of ln when we're doing calculus. Meaning is everything. Let's talk about some other properties of the natural logarithm. So here I've got our picture of the natural logarithm. It's the inverse of f of x equals e to the power of x. You could also write that as log base e or e box of x. These all mean the same thing. Since ln is a logarithm to base e, we have all the old logarithm properties holding for it. For example, there's a logarithm property that says log base a of a to the x equals x. In our case, log base e of e to the x equals x. Well, another notation for log base e is ln. So this equation is ln of e to the x equals x. That's one of the properties of the natural log, and you'll use this time and time again. Ln of x equals ln of e to the x equals x. Really, this is just a reflection of the fact that ln is the inverse of e to the x. It's going to undo what e to the x does and give you x back. Also, one of our log properties says e to the power of log base e of x equals x. Last time we expressed that as a to the power of log base a of x equals x, but with this base e to the power of log base e of x equals x. But this log base e, we're calling it ln, so we get e to the power of ln of x equals x. Again, that's a reflection of the fact that ln is the inverse of the exponential function e to the x. They undo each other, give you x back. These two properties are fundamental, and you're going to use them many, many times, and they're going to become second nature to you if they're not already. We know that log base a of 1 equals 0 always. So log base e of 1 is 0. So ln of 1 equals 0. This will become ingrained in your mind so that you don't even think about it as e box, or you don't reason it out. You just see it, ln of 1, you instantly know it's 0. We know that log base e of e equals 1, and we're going to write that as ln of e equals 1. Here's another logarithm property for log base e, but log base e is ln, so this becomes ln of xy equals ln of x plus ln of y. We have log base e of x over y is log base e of x minus log base e of y. Replace those log base e's with ln's, and you get ln of x over y is ln of x minus ln of y. Then we have this big property, ln of e of x to the power of y is y times ln of e. Log base e of x to the y is y times log base e of x, and replacing the log base e's with ln, which I just wanted to say a moment ago, we get ln of x to the y equals y times ln of x. So remember these fundamental properties of ln that are listed here, and you should work lots of practice problems to familiarize yourself with this, and they really do become second nature very quickly. You'll use them so often. Oh, and there's one more. Log base e of 1 over y is minus log base e of y. And that's really just coming from this previous line with x equals 1. And that gives us ln of 1 over y equals minus ln of y. So basic properties of ln. As an example, or an application of ln, imagine you had to solve the equation 3 to the 4x minus 1 equals 2 times 10 to the power of x. So we want to solve this for x. Find the values of x that make this equation true. When you look at this equation, the x's occur as exponents. They're way up there as exponents. And to solve it, you want to isolate the x. So somehow you want to bring those powers involving the x down so they're not powers anymore. And this is where, if you go back to our previous slide, this property ln of x to the y equals y times ln x is so useful. It tells us a power can come down in front of the ln. So what we could do to solve this equation is take ln of both sides. So take this equation, take ln of both sides. These two quantities are equal, so their ln's are going to be equal. And when we do so, using that property of ln, the 4x minus 1 will come down in front. And over here, it's ln of 2 times 10 to the x. So we might want to use an ln property to break that up further as well. Doing so, the 4x minus 1 comes down in front of the ln of 3. And on this side, we have ln of 2 times 10 to the power of x. Remember that product breaks up as ln of 2 plus ln of 10 to the power of x, using one of our logarithm properties, or ln properties, from the previous slide. Now, furthermore, this ln of 10 to the power of x, that x is going to come down in front of the ln and changes it to x times ln of 10. So in this step, all of the x's have been brought down from the power to be just factors. So next we want to solve for x, to isolate the x. And we see the x happening here and also there. So we want to collect all the terms that have an x in them on one side and combine them. And that's going to involve factoring the ln of 3 into this expression. Remember, ln of 3 is just a number. So power e has to be raised to the equal 3, after all. We can distribute that number into the parentheses here. So that gives us 4x times ln of 3 minus 1 times ln of 3 equals what we had on the other side. So now we have this x term and the one over here. Let's get those terms together. We'll subtract an x ln 10 from both sides, and we'll add an ln of 3 to both sides to get this minus ln of 3 over to the other side. And here are our two x terms. To isolate x, just factor in x out of these two terms. So it's on the outside. X times 4 ln of 3 minus ln of 10 equals ln of 2 plus ln of 3. So we can then isolate x by dividing both sides of this equation by 4 ln of 3 minus ln of 10. And we get x equals ln of 2 plus ln of 3 over 4 ln of 3 minus ln of 10. And you could probably take your calculator out and work those out and get a value for x. But I'm going to simplify things a little bit further. On top, this ln of 2 plus ln of 3, with one of our ln properties, is ln of 2 times 3. The 4 ln of 3 is ln of 3 to the 4th. That 4 can go back up as an exponent there. And then minus our ln of 10. And that gives us on top ln of 6. On the bottom, ln of 3 to the 4th is ln of 81 minus ln of 10. And now we can combine this difference, ln of 81 minus ln of 10, with an ln property. That's ln of 81 over 10. So we get x equals ln of 6 divided by ln of 8.1, which is a fine answer, but you might want to take your calculator out and get that exactly. Or, well, maybe not exactly, an approximation to like 10 decimal places. So this number, 0.8565 and so on, is the number x, where if you plugged it in up here, these two sides would be equal. And you may want to check that with your calculator. It really works. I checked it myself. So in this example, we've seen how we can apply ln to solve equations in which the variable occurs as an exponent. And you should work lots of practice with this and be sure you can do it, because you will need to do it later on when you're doing calculus. Finally, let's talk about what's called the change of base formula. The change of base formula is a formula that allows you to compute logarithms to any base in terms of ln. And I'm going to motivate this by two problems, really related to what we did on the previous slide. First of all, let's solve the equation a to the power of y equals x for y. In other words, you want to isolate the y and get it by itself on one side of the equation, everything else on the other side. Now that y occurs as an exponent, so you know you can take a logarithm of both sides to bring that down. And let's be a little sneaky here and take that a to the power of y equals x. Instead of taking ln of both sides the way we just did, let's take log base a of both sides, where a is just this base. Now, why would I want to do that? Because log base a of a to the power of y simply equals, if you bring the y down, y times log base a of a. And over here you have log base a of x. But log base a of a equals, what does it equal? Think about it. Log base a of a is a box of a. It's 1. So we get y equals log base a of x. So we successfully isolated the y in the equation ay equals x. Y equals log base a of x. That kind of begs the question, what is log base a of x? But at least we've isolated the y. By comparison, let's take this exact same problem, solve a to the y equals x for y. But this time, let's solve it not by taking log base a of both sides, but by taking ln of both sides. We should get the same answer. Taking ln of both sides, we get this. But ln of a to the y, that's going to be y times ln of a with that wonderful ln property. So we get y times ln of a equals ln of x. And finally, divide both sides by the number ln of a, and you've isolated y. Y equals ln of x over ln of a. And we've solved this equation for y. Now, notice our first solution of this equation was log base a of x, and our second solution is ln of x over ln of a. Well, it's the same equation, so the solutions must be exactly the same number. So what this tells us is that log base a of x equals ln of x divided by ln of a. And in fact, that's what's called the change of base formula. The fact that log base a of x equals ln of x over ln of a. And this formula holds for any base a and any x. And what this allows you to do is calculate logarithms to other bases of x in terms of ln. As an example, and I should point out here that before we do the example, that we could also have solved this using the common logarithm, log base 10, and the steps would have worked out exactly the same. You'd get log of x over log of a, and that would also be equal to log base a of x. But for our purposes, since we use ln so extensively, we're mainly going to think about the change of base formula involving an ln. So here's the example I had in mind. Imagine you had to compute log base 2 of 9. Well, you can't do that in your head. Well, you almost can. Log base 2 of 9 would be 2 box of 9. So power 2 has to be raised to equal 9. Well, 2 to the power of 3 is 8. So you'd expect log base 2 of 9 to be just a little bit bigger than 3, right? But it's hard to think of what it would be exactly. Well, we can use the change of base formula to calculate log base 2 of 9. Just plug in 9 for x and 2 for a. So log base 2 of 9 is ln of 9 over ln of 2. And if you take out your calculator and work that out, it's approximately 3.169925001. So as we expected, just a shade over 3. So that concludes our lecture today. We've reviewed the natural, exponential, and logarithm functions. We've talked about their properties. We've talked about applying them to solve equations, and we talked about the change of base formula. Now, to be honest, the change of base formula is something that you'll only use once or twice in calculus, but it's good to have it on your radar. Coming up next, we'll talk about, in Lecture 5D, why E is the best base. And this is actually optional. Some people are fine accepting the fact that this strange number E is just going to be very significant, and they take it on faith that it's going to make calculus simpler. And that's fine. But others want to know why this base is different from all other bases. And if you're curious about that, you may want to check out Lecture 5D. It's a short 18-minute lecture. Following that, we'll do lectures 6A and B, and they're on inverse trig functions. That will conclude our function review, part 1 of the course, and after that, we'll start doing some calculus. So that's on the horizon. I'll see you next time, and goodbye.